Okay, so the next topic we're going to go over is how can electronegativity affect pKa, and how could these substituents have an effect on pKa. Let's think about this carboxylic acid molecule. So this is a very generic carboxylic acid. This is acetic acid, and we're going to talk about just how easily this carboxylic acid can lose a hydrogen, so specifically this hydrogen right here. So we're going to be focusing on this hydrogen, and what we're going to do is think about this oxygen to hydrogen bond. And what we have to do is think about the electrons that are being shared within that oxygen to hydrogen bond. So if you think about these blue electrons specifically, you can imagine these electrons as actually being shared between the oxygen and the hydrogen. So then what we can do is maybe just kind of draw a little wavy representation of how these electrons are being shared between these two molecules. So now let's imagine a situation where we lose an H+. So we are minusing a hydrogen, and at this point, after we lose a hydrogen, we're going to get the conjugate base of the carboxylic acid. So now that you've lost the H+, you can think about where the electrons sit on the molecule. And now those electrons are now being held as a lone pair. And we had two lone pairs before, so you had this lone pair and that lone pair, and they're still there. But now we have a new lone pair. So if you think about how these electrons are localized, they've gone from a very dispersed situation right here to a little bit more of a localized situation right here. If you have this electron dispersion, you're going to increase stability. Okay, so if you wanted to talk about the stability of the molecule, the electrons are going to be much happier if they have a little bit of room to play. So if you then, let's just take the same molecule and take this molecule and redraw it over here on the right. What we'll do is draw the deprotonated form, and this is going to be our deprotonated form. You have our negative charge on the oxygen, and now what we're going to do is we're just going to add what's called an electron withdrawing group. Okay, and the whole purpose of what this electron withdrawing group is for, you can think of it as basically any group that gives you this kind of delta negative towards the EWG and a delta positive towards the other end of the EWG. And so now if you really wanted to think of and compare and contrast the electrons for this molecule right here and to this molecule right here, you can envision this EWG pulling the electron density that was localized on this oxygen more towards the EWG. So now instead of having the situation where you have a very big clump of electrons around the oxygen, you can imagine them as a little bit more dispersed again. Okay, so basically what we're doing is as soon as we tack on an electron withdrawing group, what we've done is we've increased dispersion of electrons and we've increased the stability of those electrons. And so therefore we've also stabilized the molecule. So a metaphor that I like to use sometimes for this type of situation is you have a Jack Russell Terrier. So this situation on the left would be if you had your little Jack Russell Terrier with a very small amount of room to play, versus this situation on the right is if you gave your Jack Russell Terrier a very big backyard, fenced-in backyard where it could go run around and expend all of its energy. It's obvious for the Jack Russell Terrier that this is going to be a little bit more stable situation. He's going to be a lot happier.